Good morning. Welcome to the talk about this interesting multi-producer, multi-consumer queue. And thank you for coming so early. I hope that everyone will enjoy it as much as I enjoyed writing it and the challenges that it provided for and the reasoning why we need it. So I will walk you through the reasoning why we need it, where I'm coming from, and the decisions that are needed in order to make such queue. The queue is available on GitHub, so everyone can use it. It is providing high performance, low latency, and lock-free. And we'll see we'll go through the requirement and how to use it, and how it works internally, and on which hardware operation it depends. And we'll go over them in a details soon. So this is legal about me. So I'm working in this industry many years, and I'm focused on low latency and market data distribution in trading companies. In trading companies, we will have systems that get a lot of orders and market data, and we need to make business decisions like buy or sell in a very short time. And latency is very critical in those systems. And the reason that it is so critical is because thank you very much. We have two phases. We have the phase of capturing data from the environment and making decisions. And then there is a decision. Once we made the decision, we need to send the orders, our decisions, to be executed. So all this time need to be very tightly controlled, and usually in the range of few microseconds. How do we do it? We distributed workload on multiple CPUs, and between those CPUs, we send messages using queues. So let's go to the next slide. We will go over the different following parts. We will go over trading platform a bit more. We will go over what is the environment of queues, and we will see the requirements that we have and why we need it. We will classify the different queues and see where this queue that we will see is fit into that picture of different categories. And we'll see the internals, how we do atomic lock-free algorithm that works on different compilers on x86 servers. So in trading systems, those messages that we are processing, they are being traced and tracked for very long time. That means that if I'm doing some trades today, all the logs of all the messages that were involved in this order are logged for at least a year, and we can trace down when customer complain, oh, I didn't get the execution that I expected, down to the microsecond when it happened. And this order from customer can be involving millions of dollars, and we might miss it, and we don't want to miss it. And the reasoning that we develop this type of queues is in order to be able to meet a very strict latency characteristics. And because we have multiple queues in the process, we need every one of them to behave nicely. And nicely is, we'll see in a second, is with very low latency. And when we look at the latencies, we don't want to have on the left side, on the right side of the chart, we don't want to have a fat tail, and I'll show you in a second. So let's assume that we measured the behavior of our system, and the system was doing some timing, and it was processing in order, and we got similar latencies to these samples. And you see only one of them is at the 200 microseconds, and all the rest, about 199 others, are in the range of 2 to 8 microseconds. So it seems, okay, we can ignore it. Can we? Can we really ignore such a single entry in our sample data set? So the answer is, okay, it's it's very small on the right side, right? We almost can ignore it. Look at this one. But no, if we take this diagram and turn it around a bit to a different chart, we will see something different. This is the different chart. You can see from this chart that 21% of the time was actually in that single entry. So this single entry means that our system didn't perform under the SLA, software performance requirement, certification, yeah. So we must address this type of things. So we are not allowed to have any fat tails in the histogram. And that's why we are looking always in these type of systems, what is the worst case scenario that happened from perspective of latency. And therefore, we must address these things, and we need to have control on the worst case scenario. And for that, we need a queue that doesn't behave good on the average, because good on the average is not good enough for us. We need something that behaves consistently good without dependencies on external resources. So there are no system calls in the queue. So there is no memory allocation. There is no waiting for something more than the minimum that required at the hardware level. And we will go over it. So this type of queue that we will talk about, we are describing, is non-blocking. That means that we don't see some things like that depends on scheduler. And I'll show it in a few minutes. So just to look at queues, queues in general has producers that are placing messages into the queue. The messages are waiting in the queue to be collected by one of the consumers. And different queues will have different number of producers and different number of consumers. We start with a single producer, single consumer, and we can go to multi-producer, multi-consumers. And the depth of the queue, how many messages can wait inside the queue, is also a characteristic. Is it dynamic in nature and memory is being allocated when needed, or that the fixed size of amount of memory is being allocated for the queue ahead of time? So we don't need to be dependent on memory while we are working with this queue. So, and we can see also that in this chart that we have time 0 when we are placing things into the queue, and time when we are pulling them out. We try to create those queues that if the queue is empty, the real time that the amount of time that we are staying inside the queue is very minimal. So it depends only on the hardware operations that we need to do. Okay, we talked about all these things. The queue that I'm talking about has the ability to be used both inside a process between threads or between processes, so it can be used as IPC, inter-process communication between different processes on the system. And it buffers flow of data or messages that comes in, and assuming that we have, let's just say, we have senders that are sending in a high rate, and at the same time we have a bit slower consumers. So the buffers that are inside the queue will buffer it and mitigate the problem, and will enable them to catch up a bit later. And that's why we control the capacity of a queue to be able to solve us this problem. Okay, so queues classifications. Those that are marked as bold here are those that will be our focus of that queue. So we have queues that are differentiated by number of consumers and producers. We talked about them. By the way, if you have any questions, at the end I'll be open for questions. Capacity, because we don't need, some of them can depend on memory allocation and memory then growing dynamically according to the needs. In my case, in the trading platform that we developed, we could not depend on memory allocation. Therefore, we are allocating ahead of time all the amount of entries that we will be used during the runtime. Serialization. Serialization is a very, very interesting question and topic, because different queues solve it in different way. What it means. Once I'm putting data inside the queue, am I guaranteed for a specific place in the queue? Or something that is a bit more flexible? For example, if there are queues that are based on multiple senders, single sender and multiple readers, and grouping them together. In those queues, the order will be guaranteed only within those that were sent in from the same sender. But there is no strong order between two different threads, because they are sending it together at the same time to that combined queue. Therefore, it was not good enough for our case. We needed a strong order that once I'm placing data into the queue, I know in what position I am, so I can log it. I can say, oh, this queue was, this message got this ID from the queue. So we know that it plays in the logs to know that it got a fair behavior from the system. So, and there is an issue of the API. Some of the queues have API that expose a front method, a beginning of the head of the queue, and this is not good because it is not well defined in atomic queues. So we couldn't use this. And message size is fixed in our queue that we will see a bit later. The element size that we are transferring is up to 12 bytes. Some of you will say, oh, 12 bytes is not enough for my messages, and we will see that we can transfer using it unique pointers, and once we are using unique pointer, you can transfer any message that you want. And there is okay, so let's skip the rest. Blocking, yes, that's important. Blocking and non-blocking. If we want something that will block, we have no control of how much the latency it will add to the system. So we want something that I'm trying, and if it doesn't, if the queue is full, I'm going to do something else. If it is empty, I will do something else. So we get a status on every operation that we do, and we are not entering an endless loop that will break our software. And the queue that we are using will be used, the base queue here is transferring only values. It is not transferring object types for object or for ownership of the messages that we want. to transfer, we will use unique pointers or other pointers, or we'll customize the queue ourselves. Okay, so a problem that we see in some of the queues, if we want to consider queues that are available, atomic queues that can send and receive data, we can see on the left side, we see the sender that is saying, oh, I want atomically to increase my index and place the data in that location that is mine, because I'm atomically increased the counter. No one else will get that value from that right index. But once I got this entry and I'm starting to populate it with data, I might be scheduled out by the scheduler, by the operating system. I was called out and someone else is doing the work. At the same time, someone tries to read the data. It says that there is a data, but that data is not complete because it cannot process that data. So with this type of queues that have index and data that needs to be done together, we have a problem of fat tails. Why? Because usually, most of the cases, the two lines that we see at the push, the increment of the atomic increment of the fetch and add, and the placing the entry inside the queue, they are done most of the time immediately one after the other. So the latency is very small. Nothing. We can immediately we'll see that the data is there and we will be happy and we can start working on it. But if the scheduler is hitting us in this location between these two lines, then we have a problem of the time scale of scheduler, which is sometimes in the milliseconds. So we don't want to fall into this trap. So we need a queue that should do two things at the same time. We are looking for a queue that does two things, both incrementing the indexes and placing the data into the queue. But can we do you know of any instruction that the hardware can do together, two different locations in memory to update? No, there is no such hardware operation. So we are looking for something else. We will need to look for a different algorithm that we have a single instruction that has the full information about placing the data into the queue and some notification that the index should increase. And this is part of the algorithm that we will see today. So we need a single operation that places the data into the queue, and in some way, someone knows that we need to increase the right index and to know that the data is already available and can be read without changing the index to notify about this change. And that's what we'll see today. So our requirement, I think that we covered most of them. Minimal latency, no memory, not average, multi-producer, multi-consumer, and yep. So unique requirements of the queue that we need to develop here is to have a strong ordering. So when I place data into that queue, I want to know what is my position in the queue, and with no point of argument there, and guarantee progress. We had different talks here in the conference about lock-free algorithms, wait-free algorithms, and the guarantee of progress is very interesting. It means that no thread that was blocked by the scheduler is preventing other threads from doing progress and reading or writing into the queue. So with this guarantee, this queue that we will see in a few minutes gives us this guarantee. How we do it? In order to provide this functionality, we need something from the hardware to work with. So it's not just enough to say, oh, I read, write generically. I need something that is very strong from atomic perspective. And atomic perspective means that some operations that we are going to do need to be guaranteed that they are not being stopped in the middle. So whether it is we are before the operation or the after the operation, but we can never stop in the middle of the operation. And these are things that are given by the hardware. And these operations that we have are what called atomic in C++, but the C++ atomics are not guaranteeing that the execution on the hardware is really blocking free. And if we need something from the atomic operations of the C++ to guarantee that it is lock-free always, we need to use the always lock-free. And I can tell you that some of our compilers, GCC and Clang and others, are not guaranteeing it for all data types. Of course, they cannot. Let's see an example. We can take into the atomic, in standard atomic, we can place large data, like 64 bytes or more. In order to provide us atomicity on these type of data types, we need to do a lock, do some operations, and do unlock. And in order to do atomic operations that are really atomic from the hardware perspective and from the timeline perspective, we need to use is always lock-free and use the atomics only in that case. If not, we are using compiler-generated intrinsic assembly, and you will see in the links, if anyone who wants to go to those links can see in Goldbolt, Compiler Explorer, different systems and how it is mapping different atomics from the C++ level to the assembly instructions. And some of them are here, I provided, and that's about it. So atomics, not always atomic, and without locks, just to make sure. Yeah. One atomic operation that is very, very important for our queue is compare and set, or compare and swap. The compare and swap is important because the hardware is doing it atomically. It's doing compare a given location in memory to old value that we expect to see in that location and a new value that replace it. So the compare and swap is an operation, atomic instruction to the hardware. Look at location in the memory, compare it to a given value, and if that value is equal, then place a new value into it. If it is not, don't do it. Just give us what was there before, but that's it. So compare and swap is a very interesting and powerful atomic operation. And the interesting part is that on x86, on our common hardware, we have a special type of CAS, or double width CAS. Double width CAS means that it can work on 16 bytes, 128 bits together to do the compare and swap. And this is the part of the magic that we are using here. In order to get this type of operation inlined correctly, we need to provide the compiler the MCX16 flag. Don't forget it, because then you will use by default the atomic library, which is not guaranteed to be lock-free. And if you will use the queue, and I'm encouraging everyone to use it, make sure that when you have a system with multiple CPU sockets, the reader is always on the side where the allocation of entries that we will talk in a second. that will make your queue behave better. So let's look at the design of how we design an algorithm that will solve our problem and how we define such queue. So we will create an array of entries which will be used as a circular buffer, and every entry will have few things. One is the data that we want to transfer through the queue. The other thing is an index of that specific entry in the queue, and a bit flag that tells us whether the entry is empty or full. Does it have data? If it has data that is ready to read, we will turn this bit on. If we don't have data, it will be off. So these are the type of things that we have, and we will create an array, and this type of array, and we have in the implementation a special array that knows to access the entries in a circular buffer. You can give it any index sequence, and it knows to give access to the specific entry in the queue. Therefore, we need a power of 2 entries in the queue. And each entry is changed using that CAS operation. That CAS operation, compare and swap, we are saying, oh, this is the old value, and this is the new value that we want to place. If it still has the old value, replace it with the new one. This will be the basic building block of the work that we want to do with the queue. So every operation that when we want to push data into the queue, we are looking, does it have an old value that we expect, and we'll see it. Then if it is the value, we are trying to change it to something new, and that means that we place data into the queue. Then someone, and I'm saying someone because it's not needs to be the same thread that did the push, one of the push will place the increment the right index. And the notification that the queue is now not empty and the entry is ready to be read is immediately available to the readers, because they don't look at the right index to see if there is a data into the queue, but they are looking into the entries inside the queue. We'll see it in a second. So the main API of the queue is at a very high level. I want to give a few slides about usage, because it will make us understand better what we can do with the queue. We can create it with a specific type that we want to transfer. We want to say how many bytes or how many entries, what is the capacity of the queue. And if we leave it as 0, it will be defined at the constructor. If it is not 0, we can compile it with and the template is using it with the right optimizations. Then we have index type. The index type can be 64-bit or 32 bits, and lazy, we will discuss it a bit later. So what we can do with the queue, we can create a queue, we can push values into the queue, we can pop values from the queue, we can pop values with a specific, and ask what is the ID of that element that we are receiving. We can push with index and receive the index. That's the push with the specific sequence. We get a notification what was the sequence number of the push. And a nice feature that we have is exchange. If someone is pushing data into the queue very fast, and the readers are not fast enough to read it, and we want to replace data. For example, in market data, we sometimes, if the reader didn't read so far the ticker of IBM and we care only on top of book, then we can replace that entry with this exchange operation. And we have other mechanism that keeps only a given number of elements inside the queue and remove the older entries from the queue, so we don't fail on push. Data members, we have only 3 data members in this queue. We have write index, where we are writing data into, where is the next entry that we want to write. We have a read index that the readers are using to look if there is data ready for them to read, and array that is all the entries that we want. Each entry will be aligned to a cache line to prevent fighting on at the hardware level between transferring the cache line between different reader and writers, so only one writer will access it. So the entries themselves are aligned to 64 bytes, but they are using only the first 8 bytes or 16 bytes, and we'll see it in a second. So we have an array, and here is a simple send and receive, multi-producer, multi-consumers, that pushing data into the queue and receiving data on the right side in blue. The blue are those that are receiving the data. The orange ones are sending the data, and we have multiple of them, and they send just messages which are numeric value from side to side. And it works fast, and there are benchmarks, and we'll talk about them a bit later. Okay, but I promised that there is also a way to transfer larger objects than numeric values. This is the example that we are transferring unique pointers. We are allocating in the producers. We are taking their values, and we properly transferring them through the queue. This queue is actually a wrapper around the low level that knows where to create the reset, to call the reset, and align for unique pointer. If you need to transfer other data types, you can do a similar wrapper that will use different type of operations after the move. Okay, internal algorithms for this queue is that we have the entries, write index and read index. Once we want to write data into it, we take the read index, we copy the value of it, and we look into the index, the entry in that queue, and check, oh, does it have the same sequence number? Because right now we said that we have different things inside the entries. Each entry has a sequence number inside it. That entry, the sequence number, part of it is the index of that cell inside the queue. And, okay, and we'll see in the next few slides that we can know whether the queue is full or empty by looking through the write index. We can see if it is full, and if it is empty, we can see it through the read index. And the writers never look at the read index, and the readers never look at the write index. We are having a separation here between the writers. The writers are writing into the entries in the queue, and the readers are reading from the entries in the queue and taking it out. While doing that, there is no dependency of the indexes from both sides. So here we'll have the entries that I talked about. These entries are the size, they are aligned to 64 bytes, and they have value, which is the value of that entry. It is 128 bits or 16 bytes. And it has also the data and the sequence number. Okay, the least significant bit of the sequence number is used as a flag whether it has data or not. And we have is empty, is full, for a specific entry in the queue. So we talked about this already. So this is a okay. So let's look at this one. This is a queue with 4 entries, and we have writing about it is empty. At this point, it is empty, and we start by pushing data into it. And so what we do when details. The details here, when we looked at the write index, we had 0 index value, and we approach the entry in entry 0, and we see in that entry that it is empty. So we know that we can switch the value of the entry to be full with the data and the bit flag that we said that it has data. This operation, if it succeeds, that means that no one else did it before us. And immediately after it, the reader can see that we did place data, because the flag is there, yes, there is data. And that data can be read out immediately after this operation. So even though that the switching between the slides, it was one slide, it holds 2 operations. One is placing the data into the entry, and the second operation, which can be much later, is the index, incrementing the right index. And at the same time, at that moment that we did the update to the entry, the readers can start reading the data. So we have that what happened. And here are some more details. The reader, when it is saying, oh, there is data inside the entry, and it wants to read it out, the question is what it places instead of the value that we had inside it. It will place it with no data. It will place it with 0 flag of there is no data. But the sequence number that it will put there inside that entry is now the next iteration of the loop, of the queue. So what we're getting is that it needs to put, in our case here in this queue, the sequence number of 4, because there are maximum 4 entries in this queue. So the next time that the writer will hit that first entry in the array, it will look, oh, I already placed 4 entries here, so I can place the next one in that location. So this is placing the second one. This is reading it, and you can see that the second entry got 5, which is the next iteration for that location in the queue. So here is a summary of the push. We are looking at the specific entry. We are trying to do a CAS operation on the full entry value, including the sequence number inside it, the data flag, and placing the data inside it. So this is atomic operation. This can succeed or fail. So let's look at the succeed. If we succeed, we place the data. If we failed, why would we fail? There is only one reason. Someone else placed the data there before us. That means that what we need to do is to go to the next cell, see the value of the right index, and we'll see in a second that if no one else changed it, we will change it. If someone else already changed it, we will go to the next one until we'll find an empty entry, and we succeed. If we succeed, we will go out, or we will return with success, and we know the sequence number, which is the sequence that we got from the cell or from the right index. So here is the code. It's less than 1 slide. This is the write operation into the queue. and I marked in orange those conditions between the write index and the entry sequence number and the data flag. So let's go on the first one. The first one is saying, oh, is it empty? And it has the sequence number in my write index. If it is, I'm going to try to place the data in that queue, in that entry in the queue. And I'm preparing the data that I need to place into the queue. And if I succeed, I'm trying to increase the write index because I succeed. And I'm leaving out for a second the condition on lazy. We'll discuss it later if we have time. Or the break. The second case is we got it, but it is already someone already placed the data successfully into the entry, but it wasn't me. It's someone else. So what I do, I'm helping the other to complete the other thread to complete its operation, and I'm increasing the write index for the other threads. So this is what's called collaboration. We are helping the other threads to complete their operation. And if I see in the queue, in the entry, the same, not my index, but the index of the next iteration, I know that the queue is full, and therefore I'm returning with false. So this is placing into a queue atomically. It has the iteration, but this iteration is on hardware operation only, so it is not depending on scheduler, it depends on hardware operation success. And if there is a contention, it's one for each entry and not for everything. Okay, so this is the similar, we have the operation for pop. We are looking at a read index. We are checking that the read sequence inside the entry that we got is the correct one and that the data is there. If the data is not there, that means that someone read it already. So we need to increase the read index. If not, we are reading and doing the increase. So here is the slide of how we do it. We take the read index, we load it to our local memory or registers in this case, and we are checking to see if the entry that we are pointing to has the right read value and the flag is turned on. That's why the or 1 at the end. And if it is, we see that it is empty, we see that it has the same sequence number that we are trying to read. But it has no bit, the bit of data flag is not turned on. That means that the queue is empty and we can return false. Okay, so this is the pop operation. And this is the replace operation. If someone needs to replace the value, this is, again, with a single operation, we can replace value that was waiting to be read, but it will be replaced with a new one. Here we see a single cell. What is the transition that it goes when we push data into that cell? So we can see that now it is empty. This is the first stage. Then we push data and we change it from empty to full. This is the top box. And then we pop the data and we increase the sequence number of that entry to the next iteration in the queue. This is the transitions of what we see here is the transition of each of the entries and different location in the array, and each one is jumping from full iteration of the n depending on the size of that queue. And here we see that from the perspective of time, if the entry is going through push, pop, we can see what are the values of the sequence numbers of, this is entry number 0, the first entry in the queue. Okay, so extra care that was at the design of it is that there is no place inside the queue that it is using pointers. And the reason that it doesn't use pointers, in order to place it into shared memory between different processes. So this queue can be used both between processes and with different address space and inside the and the atomic conflation is the exchange, is the replacement of old value with the new one. So testing, how we are going to test such queue? We will need to test it once in different configurations of single producer, single consumer, or multiple producers, and we will need to check that we are not dropping messages. So, for example, millions of messages are pushed in, only 9,000 are being read, or any number that is being read that it doesn't match, or duplication of messages, that no one is reading twice the same message. And so all those testing were done, and it works on Intel and AMD, and it is working and tested. And what we have in the benchmarks, we can do two things to test it. We want to test how many messages per second we can transfer through this queue. This is one type of, and we will see that we get few millions or few tens millions, depending on the configuration and how we instantiate the queue. We can, depends on the number of bytes per data type, we can transfer. If we are choosing to transfer only 4 bytes as data, for example, I have an index to a message, I have an index to some data that I want just to transfer through the queue, only the indexes. In that case, I can do with 8 bytes as entry in the queue. And that will be faster than if we have pointers or other things that require 16 bytes inside the queue. So the data size will affect our performance. Queue performance. The other type of test that we do is testing round trip time. That means that we are sending messages through a queue, and there is another queue that returns us the message back to the reader. And for that is we do in order to check the time that it took us to transfer the data through on a single clock. So the same clock that tests the source data is testing the received data. And usually it will be in below the microseconds, below half a micro for full round trip. Okay. Performance will be dependent on the CPU that we have. We are measuring the overhead of placing things into the queue and time that it takes to transfer the data through the queue. And we'll see here an example. This example shows us that we are choosing, and this was running on a laptop. It's not a high server performance. It is showing 73 million messages per second. In the case that it is a single producer, single consumer, we can indicate how many producers, how many consumers we want to use. And we can say what is the width of the data type that we want to use. And it will measure for us the performance in messages per second and the overhead that it takes to send each message into the queue. Here, and what we see in the line here is that the capacity of that queue in this test by default was 32 entries, and in the next slide we are changing it. We are using 2 producers, 2 consumers. We are increasing the number of entries to 1024, and we see we get less transfer per second, which is 11 million. And the reasoning is because we have a contention on the atomic operation, but it's still good enough in many cases. Future work on this queue is, on the left side we see the basic queue that transferred raw data. The first work that I did is to check how it will be impacted if we are taking multiple of those queues, group them together, and relax a bit the idea of strong ordering in order to get better performance, more throughput. And this enables us to increase almost linearly the throughput through the queue by packing them to a group of queues. The unique pointer transfer we discussed, it is a wrapper on top of the raw queue. Shared memory is also available between processes, and the replace and exchange in order to replace entry that was waiting too long on the queue. Multiple read of the same time data, same item. In the case of anyone who used disruptors, there is a way to convert this to behave similarly, so the same data can be read by multiple readers. But this work not implemented yet. So what did we see? And okay, what do I want to see in the future of this queue is more users. As any one of you can use it, I'll be more than happy. And drop me an email. Oh, I used it in this case, that case. I compared it to others, and I found it good or bad, and so on. It can go with the work group 21. They have a suggestion for queue, and this queue will fit to their needs. And my job is to work with them. And converting it, the CAS operation is not easily transferable to other architectures in order to get atomic operations. So the work now is to convert it to Windows, and for a second I'll talk about Windows, and RISC and ARM CPUs. On Windows, the problem is that MSVC doesn't support 16-byte data items. So there is no such extension that supports 16 bytes values. And that's something that if it needs to be ported to Windows, that will need to be addressed. And if someone can find performance improvement, more than welcome. So what did we see so far? We saw business requirements, business needs, how it impacts our needs on the queues that we are developing. We needed a strong ordering, we need no memory allocation, we needed an atomic algorithm that is lock-free, and we saw it working. And yeah, now I'm open to questions. And the other is reference. There are a few references to other queues. The queue can be downloaded, and you can test it and use it. And all the slides will be available also from last year, and the video from last year. Thank you. If anyone has questions, there are microphones here. One, right? And also there. Two, and the other one.
Okay. It's a little bit hard to reason about the things right away, but these things based on class operations, is it that, does this approach guarantee progression of every writer thread, for example? Can it be that if some thread, unlucky thread, always lose in class operation to other containing threads, that can be stuck for arbitrarily long time? Like, you can predict how long can it take.
Thank you for the question.
To perform the push.
I'll repeat the question. Is it possible that writer or reader will be starved and the others only will get the progress? Yes, a specific one, but it is very highly not likely, because this is if let's say we have 10 writers and they are trying at the same time, the one that fails, it will load again the index. And that's why the write index or the read index, so it will get a new value and will make a new decision. So it is not that we are iterating on the same without changing the index. So it is very low chance that we will wait forever. No guarantees. So there is no guarantee that a specific one will make progress, but there is a guarantee that the queue as a whole will do progress. So the whole queue will definitely will do, because someone will succeed on that CAS operation, and that one made the progress. A specific one can wait longer than. Okay. Let's take it offline. I'll be more than happy to discuss. But in production, it showed that this queue didn't have this type of problem. Yes, please, Arjun.
In one of your slides, your read and write index are separated by two cache lines. I just want to know the reasoning of that two cache line separation. Why is not a single cache line enough?
Great question. From technical point of view, the hardware in some cases will do prefetch to the next cache line when it sees that you are reading from some cache line iteratively. So in that case, it will look for the next one, and if it is fetching the next one, that will be false sharing between two CPU cores. Thank you.
So questions. I'm just curious about, have you done any testing? Compare the performance for log-free queue versus the queue with log, and I mean, like, which one is much faster?
Definitely.
And, if log-free is faster, like how many percentage, like it will be faster than the queue with log?
Thank you for the question. The question is whether I compared this performance to other queues, and the answer is yes. I can say that, for example, the answer is yes. The test benchmark that I have here, if you compile it with the specific flags, it will do testing for boost queue. I more than double the performance of the boost queue in most of the cases.
Great, thank you.
Sure.
Hey, I'm wondering if you've tested the performance on many more producers and consumers, sort of like 3264, that sort of scale.
The biggest machine I tried is with 400 CPUs, but not fully populated. But yes, we tested it. If you have a system that you want to test it on specific one, contact me and I'll be happy to see if I can help and analyze the results.
Hi. You mentioned that one of the problems with this is that the architecture needed to support a 16-byte CAS instruction. And I was just curious, what were the issues with using an 8-byte CAS instruction for a smaller queue, maybe a 31-bit sequence number and a 31-bit index.
In that case, the template is already ready and it will work on 8 bytes. So this queue can work if your data type fits into 8-byte, including the index. Perfect, it will automatically be used. And you can check the entry size and it will tell you that it is 8-byte and not 16.
Have you considered using Boost Atomic that provides a set of compile time flags for whether CAS16 is supported or not supported per architecture, and brings back the is atomic lock free back to C++ 14 at least, instead of using native C++?
I didn't find the need, and I'm not sure that all the operations that Boost is doing are lock-free in the manner that we need for this queue. But if you want, let's discuss it offline.
Okay, thank you.
Hi.
So in some of the slides, you had diagrams showing the state transitions of each cell. And in each cell, you had a state variable, which is either empty or full. And you also had a data flag, which could be 0 or 1. But in all the diagrams I saw, when the data flag is 1, state is full, and when state is empty, data flag is 0. So why couldn't they be the same flag? Why are they two different bits?
Thank you for the question. The question is why there is a bit flag that tells me whether there is data or not, and not just looking at the data field. Is it correct? And the reasoning is because I don't want to enforce on the user that there is a null value and that needs to be part of the value set. Okay? Makes sense? Thank you. Thank you very much, and enjoy the conference.